No,
I-
yo te lo he anunciado. O sea,
Tobias, Emilio, can you hear?
Fuera del...
Okay.
Hay
Now there is sound. Okay.
Sí, yo recibo.
Okay, perfect.
Está lista. Ay, hombre, usted no puede entrar. Mira, ahí tenés un...
Okay, so welcome everybody to this civic seminar. So it is a pleasure to introduce you Juan Manuel Rodríguez Parrondo. Parrondo is well known here at TIFISC. He has many friends and he has been visiting us many times in the past. For the ones that don't know him yet, he's a professor in Universidad Complutense de Madrid. And he's part also of the group GISC, Group of Interdisciplinary Physics and Complex Systems in Madrid. And so Juan is very well known from his work, so mostly from the paradox that bears his name, the Parrondo's paradox, that says that two losing games can be combined to win. And he has been working a lot also on many things like non-equilibrium phase transitions, Brownian motors. So he did a lot of contributions to stochastic thermodynamics for dissipation, irreversibility, and the arrow of time, and also the thermodynamics of information, in which the topic is written a book right now. And so we hope to read it soon. So
I hope.
He's going to talk about the second law of thermodynamics. And so please, Juan.
Okay. Thank you very much, Gonzalo. Thank you for the invitation, for being here. It's a pleasure, like always. And this is the first time I give this talk, so if there is a mistake, I hope it will be okay. And well, as Gonzalo said, I'm writing a book for many years on the Maxwell demon and thermodynamics of information, so the relationship between information and entropy and so on. And at some point, I realized that people think that the Maxwell demon problem is solved using the Landauer principle and things like that. So I don't know if you are familiar with that. The demon acquires some information, but to erase the information must dissipate heat and so on. But at some point, when writing the book, I said, no, if you go back to the original problem that Maxwell posed in 1865 or something, we are kind of cheating. We are working with most of the research on the Maxwell demon is based on the Sealer engine, which is a system in contact with a thermal bath. And when you include the thermal bath, you are including irreversibility somehow and the second law. So I had to go really back to the origins of the second law and the mechanical proofs. Well, by proofs, it's always between, I mean, it's a more rational or plus, not really formal proofs of the second law, but yeah, there are some proofs that use Newtonian mechanics. I will focus only on classical systems, although many of the things that I'm going to tell you can be extended to quantum mechanics, to quantum systems. So I will give you different proofs. Actually, I will give you 3 proofs of the second law, or 3 possible proofs. One is a Boltzmann argument that probably is the best known. The second one is based on stochastic thermodynamics, and the third one is based on a concept that was introduced in 2004, not so long ago, which is ergotropy. And these are 3 different proofs. One of the open questions is if they are related, is somehow related, and I don't have the answer. I don't know. So I will give you the three proofs. And well, Boltzmann is probably the best known. Boltzmann is based on the structure of the phase space, the space of all the microstates of a system. So each point here is a microstate of a big system, like the gas here. So it's all the velocities and positions of all the molecules in this room, for instance, in the air in this room. And probably you know the Boltzmann argument is that a macroscopic observer, well, the trajectory of my system in this phase space is very complicated. And but a macroscopic observer cannot see the details of the microstates of a system, can only see macrostates. And a macrostate is compatible with a large number of microstates. And then what Boltzmann also realized is that there are macrostates which occupy almost all the phase space. This is the equilibrium macrostate. And the other macrostates occupy smaller regions. So when you have a complicated trajectory, if the trajectory explores the phase space in a uniform way, with probability almost equal to 1, you will end in the equilibrium macrostate. And this is the Boltzmann argument that probably you have heard about even in undergraduate courses of thermodynamics or statistical mechanics. I will, and for many people, this is enough to explain the second law. Well, first, not everybody knows what is the second law. So before going into the other proofs, I will tell you some words about the second law, and especially the second law out of equilibrium, which is a problem that I think the Boltzmann explanation cannot be applied to all the possible situations that we have in non-equilibrium statistical mechanics. In non-equilibrium, especially, we can have driven systems. And in a driven system, it's not clear when you have driving, when you modify the Hamiltonian, the structure of the phase space changes. And this change in the phase space makes the Boltzmann argument not easy to extrapolate to these situations where they are driving. Also, non-equilibrium steady states, we will see that there is a problem. So this is the outline of the talk. I've shown you the first proof, which is the Boltzmann argument. Then we will discuss a little bit about the second law. And then I will show you the second proof based on stochastic thermodynamics or on information theory. It's more information theory proof. And the third one, which is ergotropy. And you can, of course, interrupt me whenever you like and so on. So what are the statements of the second law? If you go to the books of thermodynamics, you will see the classical statements, which is the impossibility of a perpetuum mobile. So the most famous one is something called the Kelvin-Planck statement, which says that it is impossible to construct a perpetuum mobile, a cycle in which you extract energy from a system in a cycle, and yeah, without any other change in the universe. So it is impossible to construct a device that operates in a cycle and produces no effect other than the extraction of heat from a reservoir. This is a classical statement. It's complicated because you have, first you have a cycle or somebody who operates, so you need an external agent. Second, you have heat. We don't know exactly what is heat, or well, we can replace heat by energy, extraction of energy from a reservoir, but we don't know. We should also define what is a reservoir. So, but anyway, this is the typical one that you find. A second one, which is a kind of popular statement, and also Planck in some book has this statement, and especially Eddington also popularized this statement, is that the entropy of an isolated system increases. But you will not see this in any book, no? Or probably you have not seen this in any book. Why? Because this is very nice to state for popular, I mean, in popular science, because it is already, this statement already indicates some irreversibility, that there is an arrow of time, and so on. But what is the problem if you want to do a serious theory with that? Is that we don't have a clear definition of entropy out of equilibrium. Let's say, an accepted definition of entropy out of equilibrium. Well, I will go back to this later on. So this is not a real problem for some of us. I mean, for me, it's a little bit a problem because I would like a theory which is autonomous without the need of external agent. And this is a real problem for the statement. So in books, you will see this one much more often than the second one. Actually, the second one. Yeah, this is what I'm. Yeah, in that cases you can. Yeah, now later on I will go. Yeah. But you cannot say that the entropy of an isolated system increases spontaneously. Well, if you start in equilibrium and end in equilibrium. Essentially, you can only define entropy in equilibrium. This is a. I recommend, if you are interested in the history of the second law and all these stories, I took this from this paper by Josh Ufking, and this is a paper with something like 80 pages, and it's about history, but also the history goes back to 1999. So he analyzes all the different statements of the second law. You have all of these. And actually, for instance, one thing that when you read this paper, and I agree in partly with the paper, is that the second law has nothing to do with irreversibility. And Ufkin argues that there are only few of the statements of the second law really incorporate irreversibility somehow. One of those is Planck's, which is the one that not the Kelvin-Planck statement, which is the impossibility of a perpetuum mobile. The Planck statement that says, Planck, in some of his writings, he wrote the second law in this way, that the entropy increases. And the lack of unanimity on the statement of the second law contrasts with the importance of the second law. This is a famous Eddington statement. I don't know if you have read this. The law of that entropy always increases, so he is using the second statement, holds the supreme position among the laws of nature. If you have a theory that is in disagreement with Maxwell's equation, well, okay, so much the word for Maxwell's equation. If you have a theory that doesn't fit with experiments, well, maybe experimentalists are wrong. But if your theory is found to be against the second law, I can give you no hope. There is nothing for it to collapse in deep humiliation. So second law is like the queen of the laws, no? Is for many people, not only Eddington, Einstein, Planck could ascribe this sentence, and even though there is so controversy. It's crazy, no? That's something that it is so strong. You have so much controversy, even in the statement of the second law. Okay, so we have said that the definition of entropy is there is no out of equilibrium entropy. I will give some words on that. In some occasions, you can define entropy in non-equilibrium situations, and as Raul said, if you have a process, you can also define, if the process connects to equilibrium states, you can also define an entropy production, if you like. There are other ways of defining entropy out of equilibrium. On occasion of Raul's birthday, I gave a talk here, and you can see the talk in my YouTube channel as well, and in the YouTube channel of the FISC, that you can define the typical Boltzmann entropy. Boltzmann entropy is the log of the volume of these macro states. You can define it, and you can even define it in an objective way. This was the topic of my talk. So you can have some kind of, you can define an entropy a la Boltzmann, and you can prove, and this is the first mathematical proof, or the first mechanical proof, sorry, of the second law, that if you have any observable, if you wait enough time, you will go to a value that maximizes the entropy. So the entropy of my system, defined in this way, will increase in time, except for fluctuations that you have always fluctuations. In the case of entropy, fluctuations are of order k. And this can be proved for any observable of your system. And this is, as I said, this is a proof of the second law in the second statement of the second law. So you can prove that the entropy defined a la Boltzmann increases in any isolated system. We should be happy because this is a proof, and many people is satisfied with this. There is a famous paper by Leibowitz that essentially said Boltzmann solved the problem of finding the mechanical proof of the second law. But if you think a little bit, and I think Boltzmann is not enough, and this is why we have to go to another proofs, and we have to look for different proofs. And the reason is the following: think of non-equilibrium situations in nature. We study. Most of you are experts in non-equilibrium statistical mechanics, and but I think I'm supposed to be an expert in non-equilibrium statistical mechanics, but I never really thought seriously on what is non-equilibrium statistical mechanics. And if you think a little bit, you will find that there are only 3 types of non-equilibrium situations. If you tell me a fourth one, I'll give you 20 euros. I pay you, I give you a bottle of Rioja. So, but I think there are only three possibilities of non-equilibrium. Probably the most known is relaxation. So you have a system in equilibrium or in a state, you change your constraints and you relax to another equilibrium state. But there are other possibilities. A second one is driving. Actually, when you study Carnot cycles at finite speed, this is non-equilibrium thermodynamics, and this is a driving system. And you can have also non-equilibrium steady states, transport, heat transport, and so on. And these are 3. Some people say, no, that there is a hierarchy of these 3. For instance, relaxation can be seen as a driven system. You have a Hamiltonian, and suddenly you change to another Hamiltonian, and then you produce a relaxation. But relaxation is a special case of driving. Do you agree? Yeah, I agree. No? You have, for instance, here you have your Hamiltonian at the beginning, and then you remove the piston, which is like changing the Hamiltonian. So relaxation could be seen as a special case of driving. Non-equilibrium steady states can also be seen as a special relaxation. Why? Because at the end of the day, it's a relaxation. When you have a hot body and a cold body, there is a transfer of heat. But if you wait long enough, the system will relax to uniform temperature. So it's a relaxation, but it's a special case of relaxation. It's a relaxation which takes very long. Why? Because the heat capacities of the bodies are very large. No? So I don't know if you are following me. I said there are 3 different situations. Many people say that all of them are special cases of the first one. So if we solve this driven system, we will solve those ones. Yeah. Okay. I think you can. No, well, yeah. There is a fourth one. A fourth one is a mixture of. You can have, of course, non-equilibrium steady states with driving. Your case could be Well, you don't need to. I think this would be a non-equilibrium. This would be a steady state. The important thing of non-equilibrium steady states is the presence of reservoirs. Not you can have non-equilibrium steady states with driving, and then they are not steady states. They are really by. So if you combine this with this, you will have a transfer of heat plus some driving. So this is not a bottle of wine. But what you have said is okay. It's super complex system. You are in the Institute of Complex Systems, but I think at the end of the day, it's a combination of this and this. If we are reductionist, I mean, if you are thinking of physical systems, yeah.
What about like the last one, but you don't have an steady state, for instance, really Bernard. I mean, you don't have just conduction, but you have rolls. I mean,
well, eventually here you can have a motor or whatever, but eventually this will I mean, if this will be a relaxation, complicated relaxation to some equilibrium state at the end of the, if the whole system is isolated. Okay, well, you can have phase transitions and things like that. Okay, I was very generous with the button. Okay, no, that's interesting. I will think about very complex systems, phase transitions, and so on. But I think they are combinations of these things. So if you think of physical systems, not isolated, because with driving you have let's say the three mechanisms were non-equilibrium, which we address in non-equilibrium thermodynamics. The three situations are these three. Anyway, I will think about that. And well, as I said, we want the proof of the second law. We want to prove the second law. So we should address all these three situations. The Boltzmann argument only applies to this one, if you think. It's very difficult. I mean, it cannot be applied to driven systems because the whole structure of the phase space changes. It depends. You have here a new time scale. So I think, well, maybe you can find a way of extrapolating this to driven systems, but I think it's not possible. Even the steady state can be considered relaxation. I think that the Boltzmann argument doesn't apply to this neither. Why? Because here you have the concept of reservoirs. And the concept of reservoir is very tricky. And it's not clear how it translates to the phase space structure. What is it? No, okay, I am a realist. I mean, I think they are finite. They are finite, but you have, let's say they are finite, but you have a period of time in the relaxation that you can consider, yeah. Okay, so this is not enough. This is here because when you drive the system, you change the structure. Actually, the equilibrium state is no longer this one, is this one. So you change the whole structure of the phase space. And I think, well, maybe you think this is impossible, but I think you have to modify it. You have to modify it completely to account for this. Huh? Yeah. No, but it's also the energy shell. So when you change the Hamiltonian, you change the energy shell. Well, we know that when you change the Hamiltonian from here to here, the whole thing changes. Even though there is even a more, let's talk about entropy production. Let's try to go to the second statement of the second law that we said that there is no entropy for out of equilibrium. But in these three situations, if you look at the books dealing with steady state, with relaxation, with driven systems, you can still define non-equilibrium entropy. Well, in this case, no. In this case, is what Raul said. You can define entropy production as the final minus the initial, because if the final and the initial are in equilibrium. Here, usually you go to any book, the Groth-Mazur or any book, and they define entropy production. How? By assuming that the reservoirs are in equilibrium. So this is also a kind of idealization. So you define, you assume that these are in equilibrium, and then you get the entropy production from the entropy change in each reservoir. And here I will show you that using Shannon entropy, you can also define entropy out of equilibrium. So nowadays, this is more recent. This is very old. You can define entropy production. And then we can try to prove mechanically the second law in the statement of Eddington and Planck, and look at the entropy production. Well, the bad news, the good news is that you can prove that the entropy production is positive. The bad news is that you can only prove it if the initial condition is in equilibrium. And in fact, what you cannot prove is that it's monotonous. You can prove that this is bigger than this, but you can have this situation. And this situation, in the case of the steady state, is very tricky, because remember, the steady state is a relaxation, very long. What if we have the steady state here? We are decreasing the entropy in a steady state. So we need a proof of the monotonicity of the entropy production. And I tell you, we don't have such a proof. We don't have such a proof. And I will tell you why. I don't know if the problem. So you can define entropy production. You can prove this. In relaxation, you can only, with the Boltzmann argument, if you think of the Boltzmann argument said only that if you start with low entropy, you will end in high entropy. But it doesn't tell you if the entropy is monotonous. It doesn't tell you if the entropy is monotonous. And the same for this guy. We will see in a moment that's the same for this guy. So this is the big problem. This is the big problem. So now let me introduce you the two other proofs of the second law. Proof always between quotes, because it is, they are not really formal proofs, but you will see it tells us a lot of what is going on in the macroscopic systems. So the first proof is stochastic thermodynamics. I prefer also to call it information theory proof, but it is a proof that appeared in the literature, of stochastic thermodynamics. So suppose that you have, I will show you the proof for the simplest case. You have a system in contact with a thermal bath, and eventually you can have an external agent driving the system like that, but it can be generalized to other things. So you have a probabilistic state. This is this whole system is isolated. So this is my probability density in the phase space. X is a microstate of the system, and Y is a microstate of the bath. So if you remember mechanics, this is X and Y obey the Newton's equations, and rho obeys the so-called Liouville equation. I don't know if you know this detail, but in many courses of statistical mechanics, one can prove that if you apply Shannon entropy, I think everybody knows Shannon entropy, no? If you calculate the Shannon entropy of this guy, you find that it is constant. So the entropy of the Shannon entropy of the state of a system, the probabilistic state of a system, isolated system, is constant. So this is not With Shannon entropy, you cannot, if you identify Shannon entropy with thermodynamic entropy, you don't find a second law. You find that it's constant, essentially. What people has done, and this is a work by Katja Lindenberg, Chris Vandenbroek, and Massimiliano Esposito, is consider this, we are going to define this entropy, which is the following. You take the marginal of this to the system. So this is the probability, this is the state of the system, and you take the Shannon entropy. And this can be out of equilibrium. And then you consider the entropy of the thermal bath, assuming that the thermal bath is in equilibrium, which is not true, by the way. But you take this object, you call this the thermodynamic entropy. This is like replacing your rho by something like that, but you don't need to invoke any observer or something like that. You just define this. This is a definition. Once you define this, you can prove that this object increases in time, always. Not increases in time. That is bigger at the end of the process than at the beginning of the process. And actually also that we call this entropy production, that entropy production is the change of entropy in the system minus the change of entropy in the bath, which is given by the Clausius. With this expression, and we prove that this is bigger than zero. Well, we Esposito in the Vandenbroek proof that this is bigger than zero. With this, you can reproduce all thermodynamics. You can prove that, I don't know, Carnot efficiency you can apply to mechanical, thermal engines, chemical engines, and so on. Of course, this is the simplest form. You can have different baths, chemical baths, and so on. But the idea is this one. By the way, the proof that this is bigger than zero is based on the fact that you can write this entropy production with two terms. One is the mutual information between the system and the bath, which is the fact that by this replacement, you are neglecting correlations between X and Y. And the second one is this one, which is the penalty that you have for assuming that the bath is in equilibrium. The bath is not really in equilibrium. The bath has some state, and the Kullback-Leibler distance between the actual state of the bath and the equilibrium state is contributing to the entropy production. So you can see this as an entropy production that comes from the fact that you neglect correlations and you assume that the bath is at equilibrium. But as I said, you don't need to do that. This is a mathematical proof. So Massimiliano told me, some time ago, no, you don't need, because in my papers you can see that I claim, no, a macroscopic observer doesn't have access to the correlations and so on. And Massimiliano told me once, Massimiliano Esposito, no, you don't need to assume that. This is a mathematical statement, and this is true.
Decomposition.
This is equal to this. This one? This one. This is not equal. This is just a replacement. This is equivalent to replace this by that.
What does the bath do? The bath doesn't drive the system, so why you use the bath?
What?
Why is the role of the bath acting upon the system?
Well, they can exchange energy. They can do whatever they. No, but this depends on time. This evolves. I mean, this guy evolves. Is affected by the bath. And also the bath, well, this is a detail. Beta depends also on time. So you have small changes of energy. This also is affected by the bath.
By what?
No, because, by Y. This is affected by Y.
By T is Roy T times something.
I don't understand the question. You have this. This is the actual state of the system where everything is. No, this is the marginal. This is the marginal. This is rho x. Oh. Rho xt is the marginal. I don't know if you can read it. It's the marginal. So it's affected by that. Okay, so by the way, for instance, in this first paper, they believe that this was the most important term, and then in a second paper, not so long ago, in 2099, they realized that this is the most important term in the entropy production is this one. Anyway. Yeah.
Like a reset of the part after the interaction.
Yeah, you could think like that. But the point is that to prove this is a mathematical proof, and actually it's 2 lines of proof. It's not very hard if you know a little bit about information theory. You need the assumption that the initial condition is uncorrelated. And since here, the initial condition, I mean, if you can, so this is always bigger than this if the initial condition is uncorrelated. Since here you have correlations, you can have a decrease in entropy production locally. And you can think, when I was writing the book, for instance, in the book you can find this proof, and I said, well, the initial condition is this one, and I never paid attention to this one. I said, well, it's reasonable that the initial condition is like that. But is this really reasonable? I mean, in a steady state, for instance, as I said before, in the steady state, you never have this. And you can have a steady state here. So the open question is, can we have periods of time where the entropy goes down and long periods of time? So this is the real question. And as I tell you, it's impossible. I mean, you can find examples where this occurs. So you start with this initial condition, the entropy is always bigger, but you can have in time periods of time where the entropy decreases. This entropy.
Periods of time is because the system and the reservoir become correlated.
Yeah. Like correlations, and then these correlations,
But whenever you apply this thing of replacing the rho, when you do that, then you have something positive. Right?
No. You can have, if you replace, you can, if this, I mean, this replacement is this one, is this definition, no? You replace Shannon and here Shannon of this, and then, and you can have, but this goes down.
Yeah, you have to replace it at the beginning and at the end.
You need to replace at the initial, you need initial conditions, uncorrelated initial conditions. Huh? No. This is not an assumption. No. Sorry, maybe this is, I forget about this formula. Forget about this formula. This is just a heuristic explanation of this. But this is, you don't need this formula. You just define this and that's.
Shannon is Gibbs.
Yeah. So what is the solution? Can we do better? Can we prove that this is monotonous? This is the problem. And the only way is if you assume some Markov approximation. I will not enter into detail, but you see, you need uncorrelated Bathan system to show that, to prove that increases. So so if you Markov approximation is like is assuming that Bathan systems are uncorrelated at any time. And Markov approximation, well, for instance, molecular chaos in Boltzmann equation is a Markovian approximation. In quantum mechanics, Born approximation. So by Markovian approximation, it's any approximation that neglects the correlation at any time. And then you can find that this is monotone. But again, in a non-equilibrium steady state, when you have two baths, it's not so clear that you can apply. People apply Markov approximation, but it's not so clear. So this is what I think we need something else than this. Because this is the typical solution, but this is not a proof of the second law, as I said. Okay. So we have a proof of the second law. We have a proof that the entropy increases, but only tells us that the entropy at the end is bigger than the entropy at the beginning, only if we start in equilibrium. Okay, this is fine, but I think it's limited, especially if we consider non-equilibrium steady states. I mean, for me, this assumption is okay. I mean, I don't have so. Okay, I can accept that at the Big Bang or something, the baths, or you start with a system in contact with a thermal bath and you start with that. The problem is non-equilibrium steady states, because in non-equilibrium states, you maybe just start like that. But if you have this behavior, you can have long periods of time with entropy, decreasing entropy. And this is, I don't like it. I mean, this is so the second, maybe how many times? There is a chairman or? You had it. 10 minutes. Okay, great. So we have Boltzmann proof, information theory proof. Now a third concept that I find very interesting, and it's for me it's also one of the best. I would say that this is the closest proof to the second law is ergotropy, and because in the previous proof you need a thermal bath and so on, so it is not for general system. This is very general. This is here. You have a system with a Hamiltonian, and the Hamiltonian depends on the parameter. And then you do a cycle. So you do whatever you like, and you, in a process of duration tau, and you go from lambda 0 to lambda 0. If you do like that, the system is isolated. So how much energy can you extract from the system? So the energy at the beginning is this one, and the energy at the end is this one. The system is isolated, so the energy that I can extract is minus the increment of energy, which is okay. Just the change of energy in the system. Okay, so what is ergotropy? Ergotropy is the maximum energy that I can extract from a given state. So the ergotropy of a state with respect to a Hamiltonian is the maximum entropy, the maximum energy that I can extract. There is no entropy here. I like this proof also because there is no entropy. So it's a maximization over all possible protocols. This concept was introduced in 2004 by Alavarjan and Valiant and Theo. No, you went. And it's amazing that it was so recent. And you can define this. So one state has a given ergotropy. Usually, instead of maximization over protocols, people define maximization over all possible canonical transformations. You know that canonical transformation is a transformation that, in principle, any evolution in any classical evolution is a canonical transformation. In quantum mechanics, you have to replace this by unitary, and this rows by density matrices, and this is a trace. But this is the same. Actually, these people introduced it for quantum systems, and there is a lot of research on this, on ergotropy in quantum systems. Gonzalo knows very well, and Roberta probably. They said that they have in this paper you can see, but I don't remember the etymology. Ergo is work. Yeah, ergo is work. So instead of entropy, they introduce this ergotropy. It's the energy that you can extract from a system. And maximum energy that you can extract. Eh? Yeah. In the first paper, in this paper, they connect ergotropy with free energy and so on. But free energy involves a bath and so on. This is mechanics. I have a rho. I can manipulate my rho. And the maximum energy is this one. Even before the concept of energy, of ergotropy, there was a concept of passive states. And but with ergotropy, it's much easier to say. There are states with zero ergotropy. So there are states where you can never extract energy from that state. These are called passive states. So states where you maximize this quantity and it's zero. So the extract energy is always smaller than zero for any canonical. So passive states are states where you cannot extract energy, and active states are states which you can extract energy from them. And as I said, in quantum thermodynamics, there are thousands of papers on that. The usual suspects in quantum thermodynamics, friends of Roberta and Gonzalo, Marcus Kuber, Mark Tipper now. I wrote this. There are like thousands of papers, but here I put only two, which are very important. Tony Athin is here also, which study passive states, and Francesco is here as well, John Gould. So you see that many people has worked on that in quantum mechanics. In classical mechanics, there is no any literature, and actually it's much harder than in classical mechanics. But anyway, I will. You can say, but are there passive states? Well, you can prove the proof is here. It's very all in the 80s. The proof is very beautiful, but I don't have time to show you that. Do you have passive states in classical systems? Yeah. If you have a probability density which is a function of the Hamiltonian, and f is non-decreasing, then you can easily prove this is the proof is very easy that this is passive. Okay. And moreover, if you impose that not only this is passive, but if you have many copies of your system and you impose that the whole system is passive, then you find that the only state that verifies this is the canonical. People is very happy with the result. They say, the canonical is the only state that you cannot extract energy from. But I'm not so happy with this because okay, it's like I want to prove the second law. So yeah, okay. So if the word is canonical, I have a second law, but I want to prove the other way around. I'm not very happy with this. And in particular, the microcanonical state, you have to remember your class undergraduate courses on statistical mechanics. The microcanonical state, which is this one, no, is you have a probability to be in a layer of energy. This is not passive. This is not passive. So you can extract energy from a microcanonical state. And actually, we have two papers. Well, there is a paper, and Chris Jarzynski also proof in a specific example that you can extract energy from a microcanonical state. So, so we are in a problem. So, in principle, you can defeat the second law, and these two papers you can think of them as violations of the second law because you have a system in the microcanonical state, which is a state that you usually use in statistical mechanics. You think that in nature, systems, isolated systems are in microcanonical states. And then you can extract energy from those in the cycle. So you can, so the Kelvin-Planck statement is not true. So how can we overcome this Well, I will give you 3 possibilities in the last 5 minutes. The first one is if you have 2 systems and the 2 systems are in the canonical state, in the microcanonical state, and then you find the marginal of 1. So you integrate. This is an exercise of undergraduate course in statistical mechanics. You find that this state is a function of the Hamiltonian. It's a decreasing function because this is the integral of, this is the volume of the layer, and this is passive. So that's fine, no? That the microcanonical is not passive, but any marginal of the microcanonical is passive, as far as you have this thing. Second example, where the microcanonical is active, but the energy you can extract is very small. Well, here you have ergotropy is very hard to calculate in classical mechanics, but there are states, the states which are uniform. This is the indicator function. So it's a rho that it is uniform in one set. A is a set and 0 otherwise. So if you have these uniform states in one set, and you have a canonical transformation, the canonical transformation is also uniform because the Jacobian of canonical transformation is equal to 1. So you go from a uniform on a set to a uniform on another set. What is the set with the less energy? If I want to extract energy, I want to drive my set A to a set with the minimal energy. The minimal energy is the one that we considered before. Is the one of this is the set of all the points with energy less than E prime. I will. We are a bit late, so I will not enter into the calculation. So you can calculate the ergotropy of any of those states. So if you apply this to the microcanonical state, you can calculate the ergotropy. You need phi, which is the volume enclosed by an energy shell. But assuming, for instance, for an ideal gas, where the volume is exponent e to the power m, where m is the number of degrees of freedom of the system, you have a very, it's very simple. I wrote the equations to show you that it's a very elementary algebra. You find that the microcanonical state is effectively passive. It's not theoretically passive. The reason is that if you remember in statistical mechanics, in high dimensional space, the volume of something is always close to the surface. So even though you have a microcanonical state with a big energy, you cannot compress this set. You cannot compress this set. So it's effectively passive. And the second, and this is my last example, I was very worried about non-equilibrium steady state. When you have reservoirs, what is going on? Well, if you calculate the ergotropy of 2 ideal gases, so the amount of work that you can extract from 2 gases with different energies, 2 identical gases at different energies, you find that the ergotropy is positive. So this is not a passive state. But what it is, you can extract energy. So you have 2 gases, no? And they are in the microcanonical, you put those in contact, you can extract energy. How much energy? This one. This one here. Look, when the 2 gases have the same energy, which is the same temperature, the system becomes passive. So you only can extract energy if they have different energies, which is different temperatures. And actually, if you calculate the entropy production and impose that entropy production is equal to 0, you get the same number as the ergotropy. Sorry, I was very fast here, but I think it's important that if you consider, and this is actually this is new. This is something that I've not published, but I think this is the a hint that ergotropy can be can tell you why you have thermodynamic limitations to the extraction of energy from a system. So I've given you 3 proofs of the second law. This is probably all of you knew this one, the Boltzmann argument. I think this only explains relaxation to equilibrium in isolated systems, but it doesn't explain satisfactorily driven system or non-equilibrium steady states. I've shown you a proof using information theory or stochastic thermodynamics. This explains the increase of non-equilibrium entropy in systems in contact with reservoirs, but assuming uncorrelated initial conditions. To really prove that the entropy always grows, you need the Markovian approximation. And ergotropy is a different approach. It's the energy that you can extract from a state. Again, we have the same thing. We can, with using ergotropy, we can prove that you cannot extract energy from systems at equilibrium. But still, we cannot prove that you can. There are states like the macrocanonical states which are active, and this is a problem. But I've shown you 2 ways of using ergotropy in microcanonical: marginals of microcanonical, macroscopic macrocanonical, and also ergotropy of non-equilibrium steady states. Open questions. Are the 3 related? I don't know. The Markovian property can be justified? I don't know. This can be extended to general states? I don't know. These are the 3 open questions probably that I have. And that's all. Thank you.
We're a little bit out of time, but we have time for some questions. Anyone?
Can I speculate?
Speculate, yeah.
Take the universe.
Oh, I was speculating for 1 hour.
Take the universe. Take the universe. The universe is in a passive state.
We don't know.
Well, you cannot extract from it. Where does it go?
What is extracting energy? Extracting energy is that an external agent modifies something in such a way that the energy decreases.
There is no external agent.
There is no external agent. Yeah.
So the universe should be in a passive state.
Yeah. Well, yeah.
Then what about irreversibility?
Yeah, I don't know. Well, I can tell you that I think, I'm not an expert in cosmology. I think the universe is isolated. There is a driving in the universe, which is the expansion. The expansion of the universe is like the expansion of a gas. Why the cosmic background is at 3 Kelvin? It went down from thousands of kelvins to 3 Kelvin.
I'm neither an expert in cosmology or I know nothing in cosmology, but my definition of universe is everything.
Yeah, but you agree that the background radiation is cooling down, and it's cooling down because the universe is expanding, and this expansion is like a driving.
No, yeah. Driving means some external thing.
No, driving means external. Okay, what is driving? Driving is mathematically that you change a parameter in the Hamiltonian. So we think of you change a field, you are in your laboratory and so on. You can also think of natural driving. What is the natural driving? The most typical is the Earth. I mean, you have the light that comes into a system. You don't need a laboratory for that. Goes up and down, night and day.
But that's something external to the Earth. There is nothing external to the universe.
Okay, but it's it's spontaneous driving. That actually you can replace any driving by a big mass with an initial velocity, which is like the Earth. Well, in this case, it's a big momentum of inertia. So you can have driving in portions of the universe. In the whole universe, yeah, I think in the whole universe the expansion is you can treat this as a driving. Anyway, you have. So I don't know if the state is passive or not. I cannot. But look at what is passive. So passive is that in a cycle. So you need the possibility of changing the Hamiltonian in the universe. So the passiveness is not. I mean, if you don't have anything to control, the state can still be active. Active is the possibility to extract. Not necessarily that you have the means to perform this extraction. It's the possibility of extracting. Yeah.
Okay, well, you gave us lots of material to think about deeply. So, but I don't quite understand the idea in a microcanonical ensemble, which is passive. So much
No,
we have
microcanonical is active.
it's active. Sorry. So in a microcanonical ensemble, a gas with adiabatic walls, it is possible to extract energy from a cycle. Can you devise a protocol to do that? Can you tell me?
I don't know, but the
Should be a
gas
different-
is active. Okay.
Can we become rich then by extracting energy out of the?
I will tell you that when we wrote this paper, it was a kind of violation of the second law.
Yes.
We have a system.
That's
we
where
have a
Roosevelt-
system. We could cool down without. I mean, extract energy from a particle in a system. What was the problem? It was a single isolated particle. So you can. We said we are doing statistical mechanics with a single particle, because the state was microcanonical, but it's a single particle. So we tried to generalize to 2-3 particles, and it was impossible. Okay. And the paper by Chris and it's also one single degree of freedom. So in principle, the theory tells you that you can extract energy. But from a gas, as you said, this is the calculation that I've done here. From a gas, this is the ergotropy of an ideal gas. And this is the number of degrees of freedom. To make this, you want this to be positive. To make this very negative, zero, you need this type of relation. This is the number of degrees of freedom. So you need a precision in your initial energy, which is the exponential of -10 to 23, which is crazy. So this is why I said the microcanonical state is effective.
So 2 questions from the people on Zoom. Perhaps Emilio, may you unmute yourself to ask?
Hello.
Or
It's
Hola, Emilio.
or otherwise.
hello. Can you hear me?
Otherwise, yeah, quick.
Yes. Okay. Thank you for
we
the
cannot
talk.
hear you.
And I have 2 questions. One is very simple. In the definition of
But I
ergotropy.
think he's trying to, because he's on mute, but we don't hear.
Can you hear me?
Maybe it's the volume of the computer itself. I know the volume itself.
Can you? Perhaps I.
Emilio,
So can you hear me or not?
Yeah, but we cannot. This is the routine. I don't know what is it.
Can you hear me?
Yes, now we can. Yeah.
Now? Okay. Sorry. So nice to see you, Juanma.
Hi, hello.
Yes, 2 questions. One, in the definition of ergotropy, is the tau, the time, is fixed? Because if not, so you are maximizing. Are
That's a
you
good question.
maximizing the protocol for fixed time, or you can also change the time?
No, that's a good question. You can also maximize over time. Actually, I introduced the concept using the cycle, no? But the definition at the end of the day, the definition is this one: a maximization over all possible canonical transformation, which implies that you also maximize over tau, and you can even, I mean, in quantum mechanics is different, because in quantum mechanics, if you have a unitary transformation, people think in the lab you can do whatever you like. I mean, you can you have a Hilbert space, you have a unitary operator, and people assumes that you have a process that implements this unitary. In classical mechanics, we are not so. So I mean, it's harder. It's not so easy. For instance, there are canonical transformations which involve changes of velocities, which are not really. I mean, in classical mechanics, the Hamiltonian is p squared divided by 2m, and this is you cannot change that. In quantum mechanics, you can change even that. But this is for any canonical transformation. This makes easier the calculation. It's not and the definition, but it's true that some canonical transformations maybe are impossible to implement in the lab.
Well, just my question was just about the time. I mean, in some formulations of second law, you assume some quasi-static, so something at very long times. I don't know. So you say that here you have also to change time, so to obtain the optimal ergotropy. Is this?
Yeah, you can change time as well.
Okay.
So it is really the ergotropy is the maximum work that you can extract by any means.
Okay.
So it's, I mean, by any means.
Okay.
But isolated, no?
Isolated.
My second question is on when you have explained the statistical thermodynamics second law, I've been lost because I don't know. You can show that the end production of entropy is positive, or can you show that the production of entropy is positive? Or, I mean, in this plot, it seems that the production of entropy is positive. So I see no problem with the second law.
No, but you need the initial. You can only prove that this is bigger than this if the initial condition is.
Yeah, okay. But in this case, you can show. So there is no, in my opinion, there is no problem that the production oscillates or it goes up and down. The entropy is always growing. Is this the case?
Yeah, it can go down. So what is the question?
No, the question is that so I don't know, why do you need the Markov approximation?
Because in the Markov approximation, at any time, you are assuming that at any time, the bath and the system are uncorrelated. So
Yeah,
I mean, by Markov approximation, I mean the typical approximation that you do to get a Fokker-Plan equation, a Lindblad equation, a Langevin equation.
But my point is, to show that the entropy production is positive, do you need Markov or not?
Yeah. In general, no. You need Markov to prove that it's monotonous.
Okay, but I see no problem.
And
If it's not monotonous, as long as it's positive, the entropy production, I don't see problem.
No. If the initial state is not this one, if the initial state is non-equilibrium or is correlated or whatever, this can go down. Which is what happens here. What happens here is that, because you can consider this is the initial state, but the state here is not uncorrelated.
It's correlated.
It's correlated.
Yeah.
Actually, the examples where you can find these are examples where the system and the bath generate correlations, and then they go down.
Okay, but I see. So I see that if the initial condition is uncorrelated, then you can show the positivity of entropy production. Okay.
Yeah, this is what I meant.
Okay.
For me, this was enough 1 year ago. Yeah. I said, wow.
But
I was writing my book. Oh my God, I'm going to finish my book in 2 months. And then in the talk, people said, no, but this problem of the initial condition is, and they are right. I mean, the initial condition is a problem. It's a big problem.
Okay, thank you, Juanma.
Thank you.
There was also a question by Tobias. So Tobias,
Yeah,
if
well,
you
well,
want-
if there's time, I don't. So, but while we have this on the screen here, so this to me, this is integrated entropy production, right? So this is S.
No.
This is not S dot, right? What is plotted here.
No. This is integrated.
This is integrated, and then I think that answers hopefully maybe Emilio's question. I don't know. That was my interpretation of this plot.
Okay, yeah. If you plot the rate, the entropy, the entropy production rate, you can have at some point here you have a negative entropy production rate, and this is a problem for non-equilibrium steady states.
Yes. So okay, but my question was a different one. So my understanding, my sort of lay understanding, the fact that we see an arrow of time in the universe, somehow there is this thing called the past hypothesis, right? That you have to assume that the universe started in a low entropy state, that you can't by dynamic arguments itself sort of argue that entropy increases in the universe as a whole. And I think that was seen as a time as a kind of controversial thing, because you don't only have a dynamic law, but you also have to make an assumption about the initial condition, which you can't explain, right? From other than cosmologists maybe can. That is related to that discussion that you had earlier.
Well, first let me clarify that I tried to do it at the beginning, but it was not very successful. That this statement of the second law does not necessarily implies any irreversibility or something like that. Actually, if you Josufkin in this paper claims that the second law has little to do with irreversibility. So that's the first point is this one. Second law has more to do with the ability to extract energy. This is why ergotropy comes in a very natural way. So, but you are right that, of course, this is some kind of irreversibility when you prove that something grows. No,
somehow the argument is if you take the state of the universe now and say what is the most likely state in the past, that past state would have a higher entropy than what you see now, right? If you assume that microscopic dynamics is reversible, then you would say that in the past, because time forward, time backward is the same, the past state would also have higher entropy than now, but that is not consistent with the arrow.
You need the initial condition with low entropy. Yeah, that's true.
That's one. Okay, and then the second point, the second remark is when you said this thing about correlations with the bath and not, this reminded me of the H theorem by Boltzmann, which he derived on kinetic grounds, and which then met some criticism, right? There was this Loschmidt and Zermelo and these people, and he had also neglected correlations in these collisions between particles somehow.
Yeah,
and I wonder if that is related to the argument that you are making somehow.
As far as I know, the H theorem is a Markovian approximation. To prove the H theorem, you need molecular chaos, and molecular chaos is essentially a Markovian approximation.
Right. But I think I thought the agreement was in the context of the H theorem and Boltzmann. This was then sort of disproved ultimately.
Sorry.
Yeah, I thought when Boltzmann made this argument based on collisions of particles, that neglecting correlations is sort of incorrect after particles have collided.
Yeah, it's not. I mean, it's not a very rigorous statement what I've said, but to prove the theorem, he has to neglect the recollisions, no? And this, I think, this is equivalent to kind of Markovian approximation where you restart at any time you are restarting with a fresh bath, let's say.
Right. Okay.
But I'm not an expert on the H theorem, but I remember when I saw the proof, it was something that is related with the Markovian approximation.
Okay. Thank you.
Okay, we are a bit late, so perhaps if you have more questions, Juan is going to be here during today. So let's go to him and ask. So thank you very much.
Sorry, everyone. Yeah, have your attention. So, maybe the on the